Shanrodi from Xiamen University, Malaysia. Today I will be presenting on a fundamental topic in mathematical analysis, the denseness of the rational numbers. We use numbers every day, but today we are going to look closely at the macroscopic gaps between them and ask, are there really any empty spaces left? Here is our roadmap. We will start with the intuition between density. Then we will establish the necessary tools, specifically the Archimedean property. After that, we will move to the core of this presentation, the proof of the density theorem. Finally, we will extend this into irrational numbers and discuss why this matters for numerical analysis and computing. Let's first start with the picture. When we look at the integers like 0, 1, 2, they are discrete, like isolated islands with big water gaps in between. But rational numbers are different. They appear to be much more packed together. So the concept of denseness formalizes this idea. It asks, in any segment, no matter how small, can we always find rational numbers? Now let's break down the concepts. As we saw, unlike discrete integers, rationals seem to fill the line. Mathematically, a set is dense in R if between any two distinct real numbers there exists an element from their sides. Why do we care these concepts? This property allows us to approximate irrational numbers like pi with arbitrary precisions. However, there is a common confusion between dense and continuous. So let's look at the notes. The continuity is like a solid roof. If you make a single card anywhere, you definitely hit a real number. While the density is different. If you make a single card, you might miss the rationals. Maybe you may hit the irrational gap like the square root of 2. But if you use two cards to size out segments, no matter how tiny the size is, you're guaranteed to capture a rational number inside. To prove this rigorous theorem, we need the tools. First, the definition of rational numbers. They are simply numbers that can be written as a ratio P over Q, where P and Q are integers. Q isn't 0. The second tool is our magnifying glass, the Archimedean property. The theorem states if x and y are real numbers and x is greater than 0, there exists a positive integer n such that nx is greater than y. So it implies that the real number system has no infinitely small elements and no infinitely large elements compared to integers. Basically, no matter how small a step size x is, if you take enough steps, you can walk past by any distance y. Now the main event is the proof of the theorem. The statement is simple. If we have two real numbers, x and y, with x is smaller than y, there exists a rational number r strictly between them. So I have broken the proof down to a simple 3-step strategy. Let's start. We assume x is smaller than y, so the gap y minus x is positive. By the Archimedean property, we can always find a huge integer n such that n times this gap is greater than 1. Then we construct an integer m is strictly between nx and ny. Let's pick m is the flower of nx plus 1. By definition, this m is just slightly larger than nx. Because our gap is wider than 1, this m must still be smaller than ny. So we have successfully captured an integer m such that m is larger than nx and smaller than ny. Finally, we divide the entire inequality by a positive integer n. This gives us m over n is larger than x but is smaller than y. Let r equals m over n. Since m is an integer and n is a natural number, r is by definition a rational number. So we have found our r. The proof is complete. So rationals are dense, but a natural question arises: what about the irrational numbers? Here we have the corollary. If x is smaller than y, there also exists an irrational number psi is strictly between them. I will briefly sketch the proof. Firstly, we consider a new interval, x over the square root of 2 to y over the square root of 2. By our previous theorem, there must be a non-zero rational number r in this new interval. Then multiply everything by the square root of 2. We get r times the square root of 2 is larger than x, but it is smaller than y. Since the product of a rational r and the irrational number is irrational, psi equals r times the square root of 2 is the number we are looking for. So why does this matters? This concept is the foundation of numerical analysis. Computers cannot store arbitrary real numbers due to the finite memory. They use floating point numbers, which are a subset of rationals. The density theorem guarantees that for any error tolerance, no matter how small, we can always find a rational approximation. For example, to approximate the square root of 2 with error 10 to the power of negative 2, we can use 1.1 to approximate. We are always safe to approximate. To summarize, the set of rational numbers is dense in the real number system. It guarantees the existence of a rational number strictly between any two distinct real numbers. The set of irrational numbers is also dense in the real numbers. These denseness properties serve as a critical conceptual bridge between discrete algebraic structures and the continuous topological structures of real numbers, underpinning core frameworks in real analysis and enabling rigorous numerical approximation of real numbers in computational mathematics. That's all for my presentation. Thank you for your attention, and questions are welcome.